Alrighty, so now a little bit of a gotcha with some probability rules. None of these are on the AAP stats formula sheet, so again, you are going to need to memorize these, but they're essentially rules that apply based on other concepts that we've already learned. So this is what we call successive events, and there are quite a few types that you could have here. So the first type is called successive independent events. Probability of A and B and yada 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 until that very last one. Well, this isn't to say that it can only be independent up to 26 events, but it just goes to show you that if the probabilities are independent of one another, the events are independent, then you just keep multiplying their probabilities. So P of A times P of B times P of C times P of D, etc. They're independent, so you just keep multiplying them. Now, the at least rule is quite a bit of a hot button topic now in the AP exam because we used to just use it for at least one. If you need at least one event to occur, that could be 1, 7, 17. The only person you don't want when you want at least one is 0 or none. So here, this is like the complement rule. The probability of at least one is just 1 minus none. But this could be at least 5, so you'd want to subtract out anyone who's less than 5. Or this could be at least 200, so you'd want to subtract anyone who's not 200, etc. Things like that. And then the last one you're somewhat familiar with through our probability tree diagrams, but this is successive dependent events, what we call sampling without replacement. So basically to find the probability of A and B, you find probability of A, but then B now becomes a conditional probability because it depends on A. And so there's some examples with marbles that we'll see here shortly. But I just want to take you here to an old AP question. And it says a complex electronic device contains 3 components, A, B, and C. And the probabilities of failure for each component in any one year are 0.01, 0.03, and 0.04. Now, if any of the components fail, the entire device will fail. So I need the entire device to not fail. So let's look at our sample space for the situation. What we've got here, and actually I had to write this on my paper here, the possibilities are all of the components fail, or perhaps the last component fails, or perhaps maybe the middle component fails, or perhaps the middle and the last component fail, or maybe we have a failure right off the bat, or maybe the failure occurs first and last, or maybe we have 2 failures in a row, but the third one's fine, or maybe all of them. Sorry, see, this is where it gets confusing because these are the probabilities they fail. So P that A fails is 0.01, meaning that A complement is that it's successful. So everything I just said need to go backwards. So we could have that the first and the third component fail, but the second component successful. We can have that all 3 components are successful. We can have that the first 2 components are successful and the last one fails. But notice that as long as there is a regular schmegular capital letter, the device is going to fail. So there's only one of these options where the device is completely successful. So I want you to keep this in the back of your head. You might be asking, Mr. Pinto, how on earth did you get all this? I actually just use a probability tree diagram. So either A happens or A does not happen. Then B happens or B does not happen. And then from there, C happens or C does not happen. And that happens for the rest of the tree. So you can see 1, 2, 3, 4, 5, 6, 7, 8 pathways that could possibly happen in this sample space. It's not very common for them to ask you to find the sample space, but being able to visualize and list the sample space is super beneficial for probability. So let's find the probability that component A will fail. So I'm looking for a capital A event, but components B and C will be successful. So I actually want this event right here. This is what I'm looking for in part B. So these are independent of one another. We're assuming they are independent, and I could have sworn it said that. But you know what? Even if it doesn't say that, guess what? We already know that the independents, right? We already know that we could just multiply along the probability tree here. So the probability that A will fail and B will be successful and C will be successful is just the product of these separate events. So successive independent events here, or possibly even dependent events, we'll see. P of A was 0.01. B being successful is the complement, so that'll be 0.97, and C being successful is the complement there. So this is going to be roughly about point something. I thought I wrote this down on my notes here, y'all. I'm struggling. Looks like 0.0093. Very small probability, but a probability nonetheless. Okay, what is the probability all of the components will fail? So now here, I want that they all have a capital letter, so that's going to be this space right here. So part C happens there, so that's just going to be the probability that, and I forgot my notation, I am so sorry, but I imagine you all are thinking A and B and C. So here 0.01 times 0.03 times 0.04 gives us an approximate probability of about very small probability here, 0.000, is that an extra one? 012. Very small probability that they're all going to fail. So we have reason to believe at least one of the components will be successful. Now here it says if the components fail independently of one another, we finally have confirmation, what is the probability that the device will not fail? So we want the device does not fail, meaning we want all successful attempts. Remember this space that I highlighted here, that is, or boxed in, that is this event here. So here in part D, I want that they are completely successful, meaning that I'm just going to multiply all the complements together. So I want A is successful, I want B is successful, and I want C is successful. I think you get the idea here, but I'm going to have 0.99 times 0.97 times 0.96. It's going to give me roughly about 0.9219. So you can see here that there's all sorts of different things they could ask you to find, and at least seeing my sample space, I can see all of these different probabilities. And because we believe this is a valid probability model, we know that all of the probabilities are between 0 and 1, and the probability of the sample space, the sums of the probabilities, should sum to 1. Now finally, last question, let's look at this at least rule, that at least one component fails. Well, if I go back to my sample space and I look, each of them has a failure except for the one where none of them fail. So I want to get rid of this on my noodle here. I just want to get rid of this last little section of the noodle. So I'm just going to subtract them out. So the probability of at least one failure is the probability, or it's 1 minus the probability that none of them fail, which guess what? We already found in part D. So that's going to give me this right here. So the probability that at least one component fails is actually quite small, which is reassuring for this device. So there you have it, a few ways you can apply at least, successive independent, and even just successive dependent events. So what I have here on the back for you are some practice problems. So word problems galore. So I'm going to let you pause the video and try these out. And then I'm actually just going to give you the answer and we'll review them in class together. The only thing I want to cover before, so that you are good to go here, would be this example here. And I'm only going to do 2 quick ones. And this is what I mean here for successive events. Suppose you have a bag of 20 marbles, 10 red, 6 blue, 4 green. Determine the probabilities of the following. With replacement, we refer to as independent, and without replacement, we refer to as dependent. That's because if I pull a marble out and put it back in, I will always have 20 marbles. But if I'm pulling one marble out and keeping it out of the bag, now I have 19. I pull another one, now I have 18. So I want to find the probability of this combo with replacement. So the first one would be 10 out of 20 would be red. So I pull that first marble. I put it back in, mix the bag around, then the next one would be another 10 out of 20, put that marble back in, then theoretically getting a blue would be 6 out of 20. And if I multiply these probabilities all back to back, then the probability of getting red, red, blue in succession altogether would be about 0.075. Not too bad. But now let's suppose I pull a marble out and then I do not replace it. So now in my first marble could be 10 out of 20. Then the probability of getting a red marble the second time would be 9 out of 19 because now there's only 19 marbles. Probability of getting a blue now, there's 18 marbles because I've already pulled out 2 of the marbles, and then there's 6. So when I take those probabilities, I get about 0.0789. So you're like, wait a second, why is it higher when you're doing it without replacement? Well, think about it, you're removing, right? You're removing some extraneous information. So each time I remove a red, it lowers my probability of getting red, you see here in the second one. But as far as my blue, now that I've removed 2 reds from that total sample space, 6 out of 18 should be greater than 6 out of 20. So you can see that increase in the probabilities there. So what I need you to do now is go ahead and pause the video and try out these remaining practice problems for yourself, and then we'll come back together and work them out. So go ahead, look over your notes, work with a partner, and try your best. Alrighty, so hopefully not too much trouble. You can see some of my work here in strategies. Again, we'll go over these in class. So you should have gotten 0.51 for the first practice problem, 0.62 for the second practice problem. Here are your respective probabilities for the customer question. I don't know how to practice wait time online because I don't know if you're pausing this and looking or you've already copied down the notes. And then lastly, here we go. We had some more of these with and without replacements. Now, the last one I wanted to go over is this one here with the airport delays. And so we've got this situation here, and I want what is the probability that the flight will have at least one of the two. So since I want at least one of the two, I'm going to find 1 minus the none. Well, if I want the none, guess what? That's only one of these 4 pathways to find that it doesn't have either a mechanical delay, nor does it have a ice delay. So I'll do 1 minus 0.7 times 0.95 because, again, subtracting that out here, that's going to give me the probability that it has neither delay. And so that is this probability here. So that's going to come out to about 0.335 that we're going to have at least one delay. So you could have multiplied along all the pathways and then added up pathway 1, pathway 2, and pathway 3. Or you could have just used the at least rule and taken out the probability of getting both delays. Because we just want, or sorry, of getting no delays. But alas, there you have all the different types of variations and rules for probability. That's going to conclude the first half of Unit 4, which is probability. And in the second half, we're going to talk about random variables and different types of discrete and continuous distributions. But for now, you have all the tools you need to be successful for this portion of the AP exam and in our AP Stats class. So I'll see you for the second half of this unit in a bit.